This video will be homework solutions to section 2.8. In section 2.8, we're asked, what does f prime say about f? In other words, what can I conclude about the function knowing something about the derivative? Up until this point, we've been given the function and we've been asked to find the derivative. Now we're going to go the other way. If I give you the derivative, I'm not going to ask you to find the function, but I'm going to say to you, or the problems are going to inquire, what can you tell me about the function if you know something about the derivative? So our homework assignment starts at problem number 1. So I'll take a look at problem 1. 1, 2, 3, and 4 are all very similar. So question number 1 says, the graph of the derivative of f is shown. And now that's very important for us to realize that. They give us a graph here, and it starts here on the y-axis. It goes through the point x is 1, y is 0. It appears to have a minimum at about here. And then it goes back through the point x is 4, y is 0. So we have a curve that looks like this. And then it stops here. This is our, and now it says, again, the graph of the derivative is shown. So our y value is the derivative, i.e. our y value is the slope of the tangent line to a curve f of x. We don't know the curve f of x. Right here, our y value is 0. That means right there, f prime of 1 equals 0. Right here, our y value is 0. So right here, that means f prime of 4 equals 0. Now they're going to ask us to draw our function. So we'll go through the problem step by step, and we'll see if we can handle each of the questions. And then those questions are going to lead us to being able to draw a graph of the function. So part A says, when is f increasing? So they want to know when our function is increasing. And we've been told in section 2.8 that f is increasing when f prime of x is greater than 0. That's our definition of when a function is increasing. So if we take a look at our graph, remembering our graph is the derivative, don't look at the graph and think, well, it's increasing over here. That's what my pre-calculus teacher said when it goes up to. That's true. That is an absolute fact. It does increase when the graph goes up to the right. But we're looking for the intervals upon which f is increasing. This is the graph of the derivative. So our definition says we need to focus on when the derivative is greater than 0. Now, if we look at our graph, right, this part here is above the x-axis. And this part here is above the x-axis. So when is our graph above the x-axis, the graph of the derivative? That's going to tell us when the graph of the function is increasing. So f is increasing on the closed interval from 0 to 1, union the closed interval from, this is 4, right? And we'll say that 1, 2, 3, 4, and we'll say this is 5 here. Then it goes on in part A, and it says, when is f decreasing? I'll use a down arrow just to speed this up. Well, we know f is decreasing when f prime of x is less than 0. That's our definition of when a function is decreasing. If we take a look at our graph, our function is below the x-axis, less than 0, here, 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 and here. And now we need to go back to part A and make these intervals open. Because the definition of increasing in our book says strictly greater than 0. So greater than, but not equal to 0. This is equal to 0. This is equal to 0. So those need to be open. This needs to be closed because that y value is greater than 0. And this needs to be closed because that y value is greater than 0. So the correct answer for part A is closed, open, open, closed. So now, when are we going to be strictly less than 0? Well, we're strictly less than 0 between 1, 2, 3, and 4. 1 and 4. Part B says, at what values of x does f have a local maximum and a local minimum? Okay. When does f have a local maximum? Well, if we think about the graph of a function, just a typical function, a function has a maximum, a local maximum, at a point such as this, right? That's what they taught us in the past. So this is a local maximum. What do I know? Well, I know over here my function is increasing, but I know over here my function is decreasing. So when my function switches from increasing to decreasing, that's when we have a local maximum. And we could reason that out by thinking about our past experience with functions. So when is our function? Now remember, we're focusing on f here. This is f prime. When is our function changing from increasing to decreasing? Well, if we look at our intervals, or if we look at our picture, increasing means the derivative is greater than 0. Decreasing means the derivative is less than 0. So we're looking for a place where the derivative goes from being positive to where the derivative goes to being negative. Well, here the derivative is positive. We said that it's above the x-axis, so that's a positive derivative. Remember, the graph is the derivative. Here the graph is below the x-axis. That's a negative derivative. So at 1, we switched from being a positive derivative to a negative derivative. That's what we're looking for. So f has a local maximum at x equals 1. Now, we don't know where that maximum is. We don't know what the y value is, but they didn't ask us that. Also in part B, it says f has a local minimum. Now, if we just flip the logic here, that means f changes from decreasing to increasing. So when does our function change from decreasing, derivative negative, to increasing, derivative positive? Well, here the derivative is negative, it's below the x-axis. Here the derivative is positive, it's above the x-axis. So that occurs at x equals 4. Then in part C, it says, we know f of 0 is 0, right? Part C, we're given f of 0 equals 0. We're actually given a point on our graph. And it says, sketch a possible graph of f. Now, why do they say sketch a possible graph of f? Well, there's a lot of answers that fit the description that we've been given so far. Typically, when we want to sketch the graph and we're given the derivative, we do it right below the graph, the derivative. It just makes things easier. So here's 1, here's 2, here's 3, here's 4, and here's 5. Now this is the graph of y equals f of x. Now the only thing we know, right, the only thing we know about our graph is we were told that f of 0 equals 0. So we know our graph touches this point. That's the only thing you and I know. Now we're going to take our information here and we're going to put this information onto our graph. When we talk about increasing and decreasing, I like to draw a bar down here like this. And I like to look at the bar and I like to go, okay, from 0 to 1, I'm increasing. So I come over here and right here on my bar, this says this isn't a graph, it's just a characteristic bar, if you want to think about it that way. So from 0 to 1, I'm going to put an up arrow to tell me my graph's going up. It's increasing. From 4 to 5, I'm going to put another up arrow to tell me my graph is increasing. From 1 to 4, my function is decreasing. That's what we found in part A. So from 1, I'm going to put a 1 here, 4 here, 5 here, 0 here. My function is decreasing. Now, if we had concavity, I would draw a second bar down below here, and I would lay out where my function is concave up and concave down. Now, we know our function has a local maximum at 1. Now, we do not know the y value for that. We just know it's a local maximum. So I'm going to come up here, and I'm going to put a dot. You can put your dot at any y value you want. It just needs to be above this, so because our function's increasing, so we have to go up to get there. Now we have a local minimum at 4. Here's 4, so I'm going to put a dot. It doesn't have to be negative. I'll just put my dot right here. There's my local minimum. Now what do? Well, we know our function's increasing, so our function's going up. That's our local max. Now our function is decreasing on the way down to here. So it's going down, and now our function's increasing. Again, we don't know how tall it goes. So this is a possible graph of f, given the information that we were provided. So now you take that information and take those steps. This layout works very nicely, and apply them to problem number 4. So the next problem I'll work on, we have 5, we have 6. Well, our assignment is 5, 7, 8, and 9, right? 5, 7, 8, and 9. So let's take a look at problem number 7. So let me clean this up a little bit. Let's take a swing at problem number 7. In problem 7, we're given 2 graphs, okay, 2 graphs. And it says the graphs of a function f and its derivative f prime are given. Which is bigger, f prime of -1 or f double prime of -1? Okay, so let's draw, this is problem 7. Let's draw our graphs here. So we have a red graph. I don't have a red pen, so I'll use pink. Our red graph has an x-intercept here and here, a y-intercept up here, and then it has symmetry. So it has an x-intercept and an x-intercept. And our graph comes down, turns, goes up, and it does not change concavity, so it just goes up like this. And over here, it comes down, it goes through, and it goes up like this, okay? And then we have a blue graph, and our blue graph goes through this point and this point. It goes through the y-axis here. It goes through here, and then it comes down through here. And so our blue graph comes through here, comes up. Comes down like this. That was my phone. Apologize for that. And then it goes like this. All right. So it says the graphs of a function f and its derivative are shown. Okay, the first thing we have to decide is which is the function, which is the derivative, right? That's our first quest here. Looking through the book and just reviewing what I've got written here, I didn't quite draw this accurately. This needs to be at a 0 right above this point. So let's see what we've got, right? Which one's f, which one's the derivative? Let's just start with a blue one and say, what if the blue one is f? Okay. Well, here my function's increasing, right? It's going up. The function's increasing all the way to here. That would mean its derivative is supposed to be positive. Well, this function's above the x-axis. Now, from here all the way to here, my function is decreasing. The blue function is going down. And the pink graph is below the x-axis. The derivative is negative, the pink graph, if that's the derivative. Now, from here over to here, my function's increasing, my function's decreasing, my function's increasing. Writing these things down below the graph really helps. And if I look in this interval right here, if I go up to the red or the purple graph, pink graph, it's positive, indicating an increasing function. Now my function's decreasing all the way to here. And my derivative is negative again. And now my function's increasing and my derivative is back positive. So that's my function. And this is my derivative. Okay. Now it asks us a question. It says, which is bigger? F prime of -1 or F double prime of +1. So we're being asked here to analyze the slopes, right? This is the slope of f at -1. That's what f prime is. It's the slope of f at -1. Now, we have hash marks on our graph, and 1 is right here, right? That's 1. And -1 oh, I'm sorry, that's not 1. On the graph, the point 1 is located here. And the point -1 is located here. And now the question is, which is bigger, right? F prime of -1. F prime of -1 is the slope of the blue line at -1, because we said the blue line was f, the derivative is its slope. So the slope of the tangent line right there is negative. What's f double prime of +1? Well, f double prime is the slope of the derivative, right? That's really two derivatives. So it's the slope, because that's a derivative, of the first derivative. When we look at the graph of the first derivative on our picture, the graph of the first derivative is positive, has a positive slope. Remember, the pink graph is the derivative. They want to know which one is bigger. So the slope of the derivative is positive. The slope of the function is negative. So the slope of the derivative the second derivative is greater. So that's how we look at problem number 7. Problem 8, we'll just work problem 8 out right over here because we have 8 and 9. 8 says, and I'll do 8a. 8a says, sketch a curve whose slope is always positive and increasing. Now remember what that means. That means the slope is always positive. Now that means f prime of x is greater than 0, and that means f is increasing. All right, that's what that means. If we the slope is always positive, the slope is the derivative. So the derivative is always positive, and the derivative being positive tells me f is increasing. But it also says the slope, if we read it, because there's an and, right? Got the conjunction and, the slope is always positive and increasing. So the slope is always increasing. Now, what does that mean? Well, increasing means the derivative. So they're telling us there the derivative of the slope. Right? We got to pay attention to the English here. The derivative of the slope. Well, the derivative of the slope, that's the slope. The derivative of the slope is the second derivative. So the second derivative is always positive. That tells us f is concave up. So I need a graph that's always positive, whose slope, pardon me, is always positive. So I need a graph that's always increasing and concave up. So a graph like this, for example, would work. Okay. Now you can do 8b and 8c. Next, we have 11, 13, and 19. 11, 13, and 19. Sorry for the pause here, but I lost my pencil. Oh, here. I found it again. 11, 13. And then from 11, I go 11, 13, 19, 23, 23, 24, 25. I'm just going to go ahead and circle all our problems here. 35, 36, 37. With the wrong line. So we don't have 11, we have 10. I'm sorry, 12, 15, 21, 12, 15, 21, 24, 25, and then 29 and 30. So we didn't do problem 8 apparently as part of our homework, but I would strongly suggest to do problem 8 because I put questions like that on the previous midterms. So let's take a look at problem number 12. Okay, because it again talks about a particle, so it ties into physics. So that's a very applicable problem to work out. So if we look at problem 12 says a particle is moving along a straight line. The graph of its position function, the distance to the right of a fixed point, is shown. Okay, so they give us a graph here for problem number 12. And we have a particle, and it's it has a local maximum at 2, and it has a local minimum at 4, and then it just goes up after that. And it starts here, it's concave down, then it's concave down until about 3, when it switches to concave up, and then it stays concave up forever. Okay. So this is our position, right? Position. So this is S, and this is T for time down here. So this tells us where our particle is located to the right of some fixed point. All right. So if we were to, because our particle is moving along a horizontal line, if we were to draw a horizontal, we'll just draw it down. If we were to draw a horizontal line here, we don't know where our particle starts. Right? There's some place that it starts. We can just call it right here, A. We don't know where that is. We don't know what number it is. They don't tell us where it starts. They're asking questions about our particle. Now, what do we know? We know our particle, this is its position, all right? So part A says, well, this is position. I guess we do know where it starts because it starts at 0. Right? It starts right here at 0. This is our position right here at time 0. This is position over here. Our position at time 0 is 0. Our position at time 2, we don't know this y value, right? We don't know that y value, but that's S of 2. That's our position at time 2. We don't know this y value, but that's our position at time 4, right? That's all we know about those values. It says, when is the particle moving toward the right, and when is it moving toward the left? When does the particle have positive acceleration, and when does it have negative acceleration? Okay. If it's moving right, what does that mean? Right? If our particle is moving to the right, that means our particle is going this way. And that means velocity is greater than 0. But we know what velocity is. Velocity is the derivative of position. So that means the derivative of position is greater than 0. That's when we're moving to the right. When are we moving to the left? Well, we know from experience, if we're going back this way, we're backing up, we're going backwards, right? Because we've defined positive direction to be to the right. So moving left means velocity is less than 0. But we know what velocity is. Velocity is the derivative of position. So we want to know, when is the derivative of position negative? It also asks us, right? It also asks us about acceleration. It says, when does it have positive acceleration? Now that means acceleration is greater than 0. But we know what acceleration is. Acceleration is the derivative of velocity, but velocity is the derivative of position. So acceleration is the second derivative of position. So we would have positive acceleration when our second derivative of s is greater than 0. Negative acceleration is when acceleration is less than 0, but we know what acceleration is. By the argument we used up here, the definition of acceleration says it's the derivative of velocity or the second derivative of position. So when we take a look at this graph, I'm going to go ahead and erase this. We're not going to need this language. what we're going to need is that approach I discussed a few minutes ago. I think it was in problem 1, I discussed it, where I'm going to make a line down here, and I'm going to talk about increasing and decreasing. Right? So I'm going to make a line, and I'm going to put down here 0, 1, 2, 3, 4, 5, 6. And I'm going to ask myself, when is this function increasing, right? Well, it's increasing between 0 and 2. From 0 to 2, it's increasing. So I'm going to put an up arrow here, and I'm going to put a 2 here, take off the 1 so I'm not confused, so I know it's between 0 and 2. When is my function decreasing? Well, it's decreasing all the way to 4. Then when is my function increasing? Well, it's increasing for every number after 4. Now, why do I care about that, right? Why do I care when my function is increasing versus decreasing? Well, because increasing is when its derivative is greater than 0. That's when a function is increasing. That's our definition one of our 4 definitions from section 2.8. So when this is increasing, when s is increasing, its derivative is positive. So what does that mean? That means this is where velocity is greater than 0 by my chain of logic over here. This is where velocity is greater than 0, and this is where velocity is less than 0. Now, when they ask me about acceleration, right, when they ask me about acceleration, what they're really asking me about is the second derivative. And we know the second derivative is concavity. That's our other definition, right? We had increasing, decreasing, concave up, concave down. So I'm going to draw another bar under here. I'm going to put my numbers down again. I've got 1, and here's 2, and here's 3, and here's 4, and here's 5, and here's 6. And I'm going to ask myself, when am I concave up and when am I concave down? Because concavity is my second derivative of position, which is acceleration. And that's what they're asking me about here. So when am I concave down? Well, I'm concave down for this part of the curve. Oh, this is concave down. It sheds water. It's concave down all the way until we get to 3. So from 1 to 3, sorry, from 0 to 3, we're concave down. Now, when do we switch to concave up? Well, we switch from here. Now we're making a shape that would retain water. We're concave up from 3 on. Now, what does that mean? Well, concavity, right? Concavity. Get those numbers off there so they don't confuse us when we go to write our intervals down. We're concave down from 0 to 3. We're concave up from 3 on. Concavity is the second derivative of position, which is by definition acceleration, which they've asked us about. So here our acceleration is negative, and here our acceleration is positive. And now we can answer question 12. When is a particle moving to the right? When is it moving left? Right? So when is it moving to the right? Well, it's moving right when velocity is greater than 0. So it's moving to the right from 0 to 2, union 4 to infinity. It's moving left when velocity is negative. That's from 2 to 4. And we can write down the intervals. For part B, it says, when does the particle have positive acceleration? When does it have negative acceleration? Well, we can see right here, negative acceleration, the interval from 0 to 3. Positive acceleration, the interval from 3 to infinity. And so that's how we work on problem 12. take a look at problem 21, 24. These are problems also that are on a lot of calculus midterms, because these problems make us show that we understand increasing, decreasing, concavity, and how they're related to derivatives. So if I take a look at problem 21, problem 21 says, sketch the graph of a function, not the function. There's many functions at work that satisfies all the given conditions. This is the kind of question on a midterm, and you have an answer that looks just like somebody else's answer, that's highly suspicious. So what do we know? We know f prime of 0, f prime of 2, and f prime of 4 equals 0. So the derivative is 0 at 0, 2, and 4. It says f prime is greater than 0, f prime, I'm just reading it from the book, is greater than 0 when x is less than 0 and when x is between 2 and 4. So we're going to use our bars down below here again. We're going to talk about when is the derivative negative. Well, over here, f prime is less than 0. What does that mean? It means my function is decreasing. Also, between 2 and 4, right? Between 2, we'll call this 2 here. We'll call this 4 here. So here's 2, here's 4, 2, 4. They told me f prime is less than 0, and that means my function's decreasing. Now, if I go on, it says, oh, I misread that. I'm so sorry. It said greater than 0 there. So my function is increasing on those angles. It's okay. When you get old, your eyes don't work as well. Now, if we look at the next line, it says it's decreasing between 0 and 2. Between 0 and 2, f prime is negative. That means my function's going down. And when I'm bigger than 4, f prime is negative. That means my function is going down. Okay. So we know all about increasing and decreasing. Now we're going to draw another line, and that's going to tell us about concavity. See if we can read this correctly. It says f double prime is positive between 1 and 3. Okay, here's 1. That's 1. Here's 3. And let me recheck. Yep, it does say f double prime greater than 0. That means concave up. It says f double prime is less than 0. If x is less than 1, right, that's 1, that's 3. So f double prime less than 0 means concave down. So less than 1 or greater than 3. Now we have to draw a graph, right? A graph. Any graph will do that satisfies these conditions. So we have the point 1, 2, 3, 4. And what do we know? We know over here, our function is increasing until it gets to 0, and then it starts decreasing, right? It starts decreasing. Then from 2 to 4, it continues going down from 2, right? It continues going, it starts going up, pardon me, at 2. From 2 to 4, it starts going up. And then it starts going down again. So our function goes up and then down and then up and then down. And we know at 0, 2, and 4, our derivative is 0. Right? What does it look like if your derivative is 0? Well, it looks like this, right? This is where the derivative is 0. That's a local max. This is where the derivative is 0. That's a local min, right? That's where the derivative, the slope is 0, the slope of the tangent line. So if we go to draw our graph, right? If we go to draw our graph now, what do we have to do? Well, we have to take into account the concavity. It's increasing until we get to 0, and it's concave down. So we'll draw a graph that's increasing and concave down. Now it starts decreasing, but it's still, look at this, it's still concave down. So it's decreasing and it's concave down, okay? But when we get to 1, right, when we get to 1, it switches to concave up. See our chart down here? It switches to concave up. But we don't switch to increasing until we get to 2, right? These are not the same point. So now we switch to concave up, but we're still going down. Increasing, decreasing. Now we start increasing, and we're going to increase all the way to 4. But we're only concave up until we get to 3. So we're concave up until we get to 3. We're still increasing, right? 3 is right here, so we're still increasing. We're increasing until we get to 4, but at 3, we switch to concave down. So we're increasing and we switch to concave down. Now from 4 on, we're decreasing and we're concave down from 3 on. So we're decreasing and we're concave down. And if we take a look at our graph, our derivative right here is 0. Our derivative right here is 0. And our derivative right here is 0, like they asked us. This chart underneath your graph is a great technique to use to try to draw these graphs. And we'll be drawing these graphs with this kind of information various places in the textbook, not just in section 2.8. All right, so that's problem 21. 24 is the same kind of idea. 25, 29, 31. Let's take a look at 29. Okay. 29 is another standard problem when we're talking about concavity and increasing and decreasing and derivatives and graphs and how the derivative affects the graph. Very standard question. In problem 29, we're given the graph of F, the graph of A, the graph of B, and the graph of C. All right. And they ask us about the antiderivative. The antiderivative. So we're going to have to do some work here to think about this. So let's draw this graph. Now, the graph of F goes just like this. It's concave up always. It's decreasing. It starts here. This is a graph of F. It's decreasing, and then it's increasing like this. This is a graph of F. Now, it says, which graph is the antiderivative of F and Y? Now, what is the antiderivative of F, right? That's antiderivative of F means whose derivative equals F. Whose derivative equals F. We have 3 graphs. We have graph A, graph B, graph C, and graph D, right? So F, the derivative of one of these graphs is going to be F. F is the derivative of someone. And so what they're asking us is the derivative of A, F? Is the derivative of B, F? Is the derivative of C, F? That's the question we're being asked. We're being given 3 graphs, and they want us to answer whose graph is the derivative of F. Whose derivative turns out to be F. So let's just draw one of the graphs, right? I have my blue pen in my hand, so we'll draw B, right? B, the graph of B goes like this. Now, is the derivative of this equal to f? The graph of c, right? The graph of c is green. The graph of c goes like this. So they want to know, is the derivative of c equal to f? Sorry, my graph of c was a little bit off. Now, what do we know about b and c? All right. And why did I not draw a? Well, I didn't draw a because we'll start with b and c. The derivative of b is the slope of b. All right, the slope of b. That's the derivative of b. The slope. Derivative of b means the slope of the blue graph. The slope of the blue graph right here is positive. The slope of the blue graph right here is positive. The slope of the blue graph right here is positive. The slope of the blue graph right here is positive. And if I drew this graph correctly, its 0 is right there. Then the slope of the blue graph over here is negative, and it's negative, and it's negative. So if we were going to do our chart for B down here, and we were going to talk about where it's increasing and where it's decreasing, right? Where it's increasing and where it's decreasing, we would go right to here, this point right here, and we would say over here, the derivative is is less than 0, which means it's decreasing. Over here, the slopes are all positive, so the derivative is greater than 0, which means it's increasing. Well, does f fit that? Right? Does f fit that? F is decreasing. So the derivative is less than 0. Looking at my picture, the 0 is supposed to be right here, isn't it? That's where I said the 0 was, so we need to move this over here. There we go. Now, the derivative is less than 0, so the function is decreasing. The function will be below the x-axis, right? And then over here, the derivative is greater than 0, so that means increasing. So we want to know, is the derivative of b equal to f? Well, does f satisfy those conditions? Is f negative here and positive here? We're talking about b, not f. The derivative of b is negative here. The derivative of b is positive here. Now, does f satisfy that condition? Is f negative here? Yes. Is f positive over here? Yes. So the derivative of b equals f, which means b is the antiderivative of f. We're going to talk about antiderivatives throughout all of chapter 5. This problem is just a little foreshadowing of what's coming down the road. Don't worry, they'll be a lot easier when we get to them in chapter 5, because we'll be a lot further along in our understanding of calculus. All right, so that's our video on 2.8.